Hi, and welcome to Allen High School APIB Chemistry. We're in the midst of our discussion of thermochemistry and thermodynamics. We're going to move into constant volume calorimetry. Now, when we're talking constant volume, we can't really be equating delta H and Q anymore. That's not a valid equality, so we're just going to stick with Q. Now, in a calorimeter, in a bomb calorimeter, typically what you have is water in a metallic, very tightly sealed system here, and you put your sample separate. So that's one thing that's nice, is that the boundaries between your system and your sample are very well defined, unlike solution calorimetry, in which there's really a bulk solution and the reaction point of interaction is where your system is. We don't have that this time. They're very distinct. So what happens is you put in pure oxygen. So there's a source of oxygen. You see this in your picture, an oxygen inlet, excuse me. You put your sample in here, whether it be, let's say, a Butterfinger bar or pizza. We can determine actually the caloric amount in foods by doing this. There's an ignition wire, because even though it's exothermic, we still need to overcome that initial activation energy. And then we have your thermometer to measure your temperature, and you want it that it's stirred and so on and so forth. So now heat is going to leave the sample because combustion is exothermic, and it's going to be absorbed by the water, and it's also going to be absorbed by the components of the calorimeter itself. So Q of combustion is going to be equal in magnitude but opposite in sign, right? If one releases, the other absorbs energy. Q of the water plus Q of the calorimeter. Now, you have to be careful here, because there are times in which the water is already included in the calorimeter constant itself. So you have to read the context of the question to see what information they're giving you. In the past, we neglected this. It's possible that this has been wrapped into this one, and that's all we have, that the water has been wrapped into the calorimeter. So you have to evaluate the information that's given to decide what you have to do for these problems. So let's take a look at one. We're dealing with octane C8H18, primarily constituent of gasoline. Now, you want to highlight a few things, because when we calculate this, we're calculating what we would have for a 1 gram sample. Now, that 1 gram sample is part of the system. It is not part of the surroundings. So you're not going to include that 1 gram sample in the mass of your surroundings. Now, some other important information that is given that's valuable is we have 1.20 kilograms of water with the heat capacity of the water. So it's clear in this case that the problem separated out the two parts, the water from the calorimeter constant itself. And it tells us that the heat capacity of the calorimeter, notice how much larger this value is. That's because that 837 includes the mass of the calorimeter, all the components and the large calorimeter itself. So mass has already been included in that, whereas for the water, the mass is separate. So let's take a look at this. Q combustion is going to be equal in magnitude but opposite in sign, because a combustion is exothermic. It's going to release energy, which means that the water and the heat capacity, the calorimeter are going to gain energy. So for my water, I'm going to convert that to grams, because I've got grams here, and 4.184. My temperature is going to be final minus my initial, so it was 33.2 minus 25. Doesn't go up a whole lot. The heat capacity of water is actually pretty high, and so it takes a lot of heat energy to raise water, a gram of water, 1 degree Celsius. Well, we have way more than 1 gram. We have 1,200 grams. So the temperature really doesn't go up that much. And now it's the calorimeter constant. Remember, it's just MCAT and CAT, if you want to think of it that way, because the calorimeter constant includes the mass, so we don't need to worry about that. But it's assumed to be in thermal equilibrium with the water itself, so that temperature change is the same. Now, if I solve for this, I get minus 4.80 times 10 to the fourth joules for that sample. So in our example, that was for a 1 gram sample. All right, it wasn't joules total. This is how I like to do mine. Some people like to just convert mass to moles using molar mass and then do the division. I like to put that underneath here because it was minus 4.8 times 10 to the fourth joules per 1 gram sample. I need it on a per mole basis. And so I'm going to convert that. And by the way, that was the kilojoules per that 1 gram. I'm going to convert mass to moles using molar mass. Get my grams to cancel. Mass to moles, use molar mass. If I calculated it right, it's this value here. And then it did say kilojoules, so I'm going to go ahead and do that kilojoule conversion right here. Okay, so we had 2 possible answers here. We had our first answer, that was in joules. All you had to do is convert that to kilojoules to get this. And now, if I solve this, this part here, the part 2, so this is part 1, and then the part 2 comes out to be minus 5.4. I got 80. I think it's just where rounding occurred within the context of the question. And so that would be our second answer because it was a 2-part question. Okay, so that is using a calorimeter. That finishes up using MCAT for now. We're going to move into a discussion of Hess's law. And I think it would be a good idea to move into a new video for that. So until then, this is signing off.